Hi, so this is problem 10.3 at page 620, and we are in this problem related to vapor refrigeration system. So in this problem, we are told that we have a Carnot vapor refrigeration cycle operates between thermal reservoirs at 40 degrees Fahrenheit and 90 degrees Fahrenheit. For A, refrigerant 134A, propane, water, refrigerant 22, and ammonia as the working fluid. Determine the operating pressures in the condenser and evaporator in pound-force per inch squared and the coefficient of performance. Alright, so here first thing, let's write what is given. Here we are in this problem we're dealing with a Carnot vapor refrigeration cycle. And this is an idealized refrigeration cycle based on the principle of the Carnot heat engine. It is reversed to achieve refrigeration or heat pumping. Although not practical for real-world application due to its limitation, it serves as a benchmark for evaluating the performance of real refrigeration system. And we are told that this Carnot vapor refrigeration cycle operates between two thermal reservoir temperatures. The first one is T sub C, which is the heat absorbed from the cold reservoir, and the temperature of the, so this is the low temperature reservoir or cold temperature reservoir, is the temperature at which the refrigerant absorbs heat during the evaporation process. T sub H is the heat rejected to the hot reservoir. We call it high temperature or hot temperature. Is the temperature at which the refrigerant rejects heat during the condensation process at 90 degrees Fahrenheit. And we are told that the working fluids that we need to find the operating pressures on it is these ones. All right. So what do we need to find? We want to find the operating pressures in the condenser and the evaporator for each working fluid. So what we want to find is at the evaporator, what is happening in the evaporator? The evaporator is changing phase between liquid and from liquid to vapor. And in order for this to happen, the temperature of the working fluid must be at a saturation temperature. So the 40 degrees Fahrenheit is the saturation temperature. So the question is, what is the corresponding saturation pressure? And the same thing we want to do for the condenser at 90 degrees Fahrenheit. And the second thing is we want to find the coefficient of performance, or we call it the Carnot cycle coefficient of performance. So this is the COP is the maximum theoretical coefficient of performance of any refrigeration cycle operating between the two regions T sub C and T sub H. It's a good practice to draw schematics. It will help us visualize the problem. So here I will have two schematics. First, a drawing of the Carnot vapor refrigeration cycle, and a graph that represents the Carnot vapor refrigeration cycle. We will have the temperature here in degree Fahrenheit, and here we will have the entropy. Now, from what is given to us, this Carnot vapor refrigeration cycle operates between two thermal reservoirs at 40 degrees Fahrenheit. So here the working fluid enters the evaporator at a 40 degrees Fahrenheit, and this is the saturation temperature because phase change happened from liquid to vapor at the evaporator. And the next reservoir is the hot reservoir or the high reservoir at 90 degrees Fahrenheit. That's the at this temperature the heat is being rejected to ambient, and so the working fluid enters the condenser at 90 degrees Fahrenheit, and what does the condenser do? It changes phase from liquid to, from vapor to liquid. So this is a saturation temperature. So again, we want to find the saturation pressure for a saturation temperature 90 degrees Fahrenheit and the saturation pressure for a saturation temperature of 40 degrees Fahrenheit for each working fluid. And finally, we want to find the maximum theoretical efficiency of this Carnot vapor refrigeration cycle operating between these two thermal reservoirs. So here we want to find the solution for refrigerant R134A, this working fluid. And remember, we are given these two thermal reservoirs. So what we will do is we will go to table A-10E, which is properties of saturated refrigerant 134A liquid vapor temperature table, since we are given temperature at page 957. So we will go to this table, we will go to the temperature, which is in degree Fahrenheit, then we will go to the 40 degree Fahrenheit. So the corresponding saturation pressure is 49.738, which is in units of pound-force per inch squared. So here we will write down the evaporation value, the operating pressure at the evaporator. Now, within the table, we will go all the way down to 90, and the corresponding operating pressure is 118.99. And we will do the same exact thing for the other working fluids, but pay attention to the different operating pressures that you need for different working fluids. So this one is propane. Let's see, will we need more pressure or less pressure? So again, these are the two temperatures, reservoirs. We will go to this table, A-16E at page 968. Temperature table, degree Fahrenheit, 40. We're going to need lower, 78.6, and no, higher, sorry, 90, 165.2. So here we will write down these two pressures. So these are the two operating pressures for this working fluids at these two thermal reservoirs. C is water. We will go to table A-2E, page 939. The temperature 40, 0.121. So we need like a vacuum pump in this case. And the 90 degree is 0.6988, around 0.7. And here we will write down the operating pressures for the evaporator and the condenser, having the water as our working fluid. D, refrigerant 22. Again, these are the two temperatures that we're dealing with. Then we will go to table A-7E at page 951. The temperature 40. So the operating pressure, so the refrigerant R22 must enter at a pressure of 83.278 in order for it to start to evaporate at 40 degree Fahrenheit. 90 degree correspond to it is 183.16. Now for ammonia, we will go to table A-13E, page 962. Same exact thing, 40 degree Fahrenheit, 73.359, and 90 degree Fahrenheit is 180.73. And here we will write down these two operating values. Now the coefficient of performance. I remember, in a refrigeration cycle, the efficiency ratio is typically referred to as the coefficient of performance COP, which measures the ratio of cooling effect produced, or in other words, heat removed from the cold region, to the energy input required, work done by the compressor, or the net work of the whole cycle. So here we have the two thermal reservoir temperatures, and this is our temperature entropy diagram. So let's remember, what is efficiency? Efficiency is the output or the desired value over the given value or the input. So what is the output? What are we desired to do in this cycle, in this refrigeration cycle? We want to absorb as much heat. We want the refrigerant or the working fluid from state 4 to state 1 to absorb as much heat from the conditioned space to cool it down, right? So this is the output. So this is the cooling effect. And we want to find the input is how much work we need to put into the system in order for it to operate. So in this case, in a Carnot vapor refrigeration cycle, from 1 to 2 is the compressor, and from 3 to 4 is the turbine. Or in other ways, the energy that's being absorbed by the working fluid minus the refrigerant that's being rejected, or sorry, minus the heat rejected by the refrigerant in this case. So we can say Q sub C work or the net work, and the net work can be found by the difference of Q sub H minus Q sub C. So remember, Q sub C is the heat absorbed by the working fluid, and Q sub H is the heat rejected by the working fluid. So the maximum theoretical energy, and here from thermodynamics, the heat transfer, which is in this case Q sub C and Q sub H, are proportional to their respective reservoir temperature, T sub C and T sub H. So in this case, we will plug in the values that we are given, and here we can find that the maximum coefficient of performance is 9.98. And again, this is the maximum theoretical coefficient of performance, meaning the real refrigeration cycle, or what we call it the vapor compression refrigeration cycle, it will have a lower value. And as engineers, what we try to do is so for example, when we take that real value, real refrigeration cycle that we will discuss in the future, where this real refrigeration cycles operate between these two temperatures, 40 degree Fahrenheit and 90 degree Fahrenheit, we try to design this cycle in order to achieve this maximum efficiency or maximum COP 9.98. And again, we use it as a benchmark. Problem 10.4. So in this problem, we are told to consider a Carnot vapor refrigeration cycle. We still deal with a Carnot vapor refrigeration cycle. And the working fluid is refrigerant 134A. The cycle maintains a cold region at 40 degree Fahrenheit when the ambient temperature is 90 degree Fahrenheit. Data at principal states in the cycle are given in the table. So there's a table that I will show. So remember, this is data. So this is a Carnot vapor refrigeration cycle, and we have a measurable data for this cycle operating at these two temperatures. In the cycle are given in the table. The states are numbered as in figure 10.1, which I will show. Sketch the temperature entropy diagram for the cycle and determine the A, temperatures in the evaporator and condenser, each in degree Rankine. So we already have the temperatures in degree Fahrenheit. We can easily use the conversion factor. We want to find the compressor and turbine, each in PTU per pound mass. Or in other words, the specific work for the compressor and the specific work by the turbine of refrigerant flowing. C, coefficient of performance. D, coefficient of performance for a Carnot cycle operating at the reservoir temperature. So C basically is asking for the actual coefficient of performance. And remember, we are given measurable data, and we can use this measurable data to find the actual. And the maximum theoretical, we can use the thermal reservoir temperatures. So first thing we are given we are dealing with a Carnot vapor refrigeration cycle, and remember, it is an ideal cycle. The working fluid that we're dealing with is refrigerant R134A, and this refrigeration cycle operates between two regions, cold region and ambient or hot region. The cold region at 40 degrees Fahrenheit and the hot region at 90 degrees Fahrenheit. So that's the working fluid temperatures. And here we are given this table. This is measurable data from a Carnot vapor refrigeration cycle, and this is the figure that the problem statement talked about, which is the temperature entropy. And as you can see in here, from state 1 to state 2, at state 1 the pressure is 40 pound-force per inch squared, and as you can see, this is specific enthalpy. And remember, what is enthalpy? Enthalpy is the internal energy, and remember, internal energy is affected by change in temperature. So as temperature change, you have higher internal energy, and vice versa. So it's internal energy plus the work. So going from state 1 to state 2, so we said, remember also that is specific enthalpy or enthalpy, another word that we can use, or phrase that we can use to describe enthalpy, is energy content, the energy content of a working fluid. So from state 1 to state 2, which is state 1 to state 2, this is a compressor. So what does the compressor do? The compressor increases the pressure. So as you can see from this table, it was 40, it became 140, and it increased the temperature. So that is why the enthalpy value increased from 104.12 to 114.95. Then this working fluid enters the condenser from state 2 to state 3 at a constant pressure. You see 140, 140. All right. And what's happening in the condenser? The condenser is changing phase from from vapor to liquid. And what's happening in here is there is heat rejection. So because of that, the energy content will decrease to 44.43. And then from phase 3 to phase 4, in this Carnot vapor refrigeration cycle, we have a compressor. So from 3 to 4, the compressor reduces pressure and reduces temperature, and that's why, as you can see, pressure 140, the temperature, the turbine reduces the pressure to 40, and it uses it to produce work. So the energy content of the fluid decreased from 44.43 to 42.57, and from 4 to 1, that is your evaporator, where we change from liquid to vapor, and as you can see, 4 in here is mainly liquid. We are closer to the liquid region, to 1, which is mainly vapor. And as you can see, in when the working fluid exit the evaporator, it exit mainly mainly vapor, but it have some liquid. Having a liquid in a compressor is not a good idea, and that's why the Carnot vapor refrigeration cycle is not realistic cycle, and that's why I said in the beginning we can use it as a benchmark only. So from 4 to 1, what's happening is we absorb heat, so that is the cooling effect. So we go from 42.57, heat is being added, or sorry, heat is being absorbed to change phase, and it exits at a higher energy content of 104.12. Now, what do we need to find? We are asked to sketch the temperature entropy diagram for the cycle. We want to find the temperature of the evaporator and the temperature of the condenser in degree Rankine. We want to find the specific work of the compressor and the specific work of the turbine. We want to find the coefficient of performance, actual one, from the data given, that measurable data, and we want to find the maximum theoretical one. Just like before, we will have a schematic, and we will write down what is given to us, so we can sketch it and be able to visualize it. And remember, we are given the condensation pressure for the condenser and the evaporator, and we want to find the specific work of the compressor and the specific work of the turbine. This is the input work, this is output work. So subtracting them will give us the net work. Now, the first thing we are asked to find is to sketch, and this is our sketch, the temperature in here and entropy in here, and we will draw the liquid line and the vapor line meeting here at the critical point. They call it the dome, and this on the left side is the liquid region, two-phase region, and superheat region. And here we draw our Carnot vapor refrigeration cycle. Now, for solving number A, we want to change the temperature from degree Fahrenheit to Rankine. So we will use the conversion factor, which is 459.67 to 40 degree Fahrenheit, and that's the value 499.67 degree Rankine. And we will do the same thing for the 90 degree Fahrenheit by using this conversion factor. Now, the solution for B. Now, what do we need to find for B? We want to find the specific work of the compressor. So remember, we said that from 1 to 2, that's what? That's the compressor. And we have the energy content in PTU per pound mass. So from 1 to 2, it starts at 104.12, and the compressor increases the pressure to 114.95. So we will take the difference between them, and that will give us the work input by the compressor, which is 10.83 PTU per pound mass. Now, the work of the turbine, same thing. The working fluid, the energy content of it at state 3 is 44.43, and the energy content of the working fluid at state 4 is 42.57. And what does the turbine do? It reduces the pressure, and it gives us an output work. So we will take the difference between it, 44.43 and 42.57, and the work output is 1.86 PTU per pound mass. All right, so here we want to solve for C and D. So this is, we want to find the coefficient of performance. So let's recall. The Carnot COP represents the maximum theoretical efficiency. Real systems have lower COPs due to irreversibilities like friction, non-isentropic compression, heat losses, and imperfect heat exchange. The second law of thermodynamics is useful in defining the maximum performance of real processes and cycles. A reversible process is a hypothetical limit for real processes and represents either the maximum possible work production or the minimum possible work production. Now, reversible all right, so the COB, or the efficiency ratio actual, will be the cooling load divided by the difference in the specific work of the compressor minus the specific work of the turbine. And remember, the values that we will get for Q sub C, the cooling load, and the compressor and the turbine, these values we will get it from the measurable data that we are given. So there is something that in reality, the actual cycle, these data took into consideration that there is friction, there is inefficiency in heat transfer. That's why we call it actual. So the COB actual, and remember, cooling load is the difference between how much heat is being absorbed from state 4 to state 1. So from state 4 is 42.57, it absorbed heat and it become 104.12. So that's the difference. Minus, divided by the work of the compressor, that's the input work, minus the output work from the turbine. So COB actual will be 6.86. Now the maximum theoretical one, just like we did in the first problem, is the difference is that we use the thermal reservoir temperatures in here. So we will plug in the thermal reservoir temperatures that we are given, and the maximum is 9.98. So the difference here between the theoretical with thermal reservoirs 40 degree Fahrenheit and 90 degree Fahrenheit, the maximum efficiency ratio, or COP, coefficient of performance, is 9.98. Now when we have this refrigeration cycle and in real world, and we operate it at these temperatures, at these pressures, and with the given thermal two thermal reservoirs, from these collected data that took into consideration that in reality there is friction, there is loss in heat, there is inefficiency in heat transfers and other things. From the actual data we get that the COB is 6.86. so that's mean we need to redesign and see how can we reduce friction, how can we make the heat transfer more efficient to get the actual refrigeration cycle that we have as close as possible to the maximum theoretical one. Thank you very much.